Hello everyone. So this is the first hour when we talk about thermodynamics. Students ask me many a time, sir, how to solve question of thermodynamics quicker? And I have the same standard answer, memorize each and every process. So in this hour, I will make you remember all the processes. What are the equation? Which equation has to be used? You will get it given that you remember the equations. So without wasting time, let's start this hour. In this hour, we will talk about the zeroth law, the first law, as well as some standard processes. So without wasting time, let's start with the zeroth law. So what does zeroth law tells us? From zeroth law, we actually get the definition of temperature. Let's say we have got three bodies, body A, body B, and body C. As you can see in the figure, body A and B are separated by an adiabatic wall. When I say that adiabatic wall, what is the meaning of it? Adiabatic walls are made up of non-conducting material. So there is no heat transfer across the adiabatic wall. While A and C as well as B and C are separated by diathermic wall. Diathermic walls are made up of conducting material. Every time I say adiabatic wall, think of ceramic walls. The wall made up of ceramic will let only very small amount of heat to pass through it. And whenever I say diathermic walls, think of walls made up of metals. Through the metals, the heat can flow easily, right? So when you have got these three bodies such that A and C and B and C are separated by diathermic walls, then over the period of time, A and C will attain thermal equilibrium. It means that no net heat flow will take place from A to C and C to A. Similarly, as B and C are also separated by diathermic wall, over the period of time, B and C will also attain thermal equilibrium. So what does the statement say? Statement says, if A and C are in thermal equilibrium, A and C are in thermal equilibrium, and B and C are in thermal equilibrium. So given that A and C are in thermal equilibrium as well as B and C are in thermal equilibrium, this means that no net heat exchange takes place between A and C and B and C. Then if placed together, A and B will also be in thermal equilibrium. So if you take out A, if you take out B, place them side by side, then no net heat transfer will take place between A and B. So this is the zeroth law of thermodynamics. Zeroth law gives the idea that for bodies to be in thermal equilibrium, their temperature should be same. So whenever we say that A and C have attained thermal equilibrium, this means that now both of them are at same temperature. So zeroth law gives the idea that the bodies to be in thermal equilibrium, their temperature should be same. So zeroth law actually gives us the idea about temperature. So now let's move on and start understanding some terms. So first of all, heat. What is heat? Heat is the energy in transit. So heat is the energy in transit. Heat flows from the body of higher temperature to the body of lower temperature. So let's say you have got a body at a temperature T1, another body at temperature T2. Let's say T1 is greater than T2. A net heat flows from T1 to T2, the first body to the second body. The energy in transit is called heat. When this energy was with the first object, it's called the internal energy of first object. When this energy reaches the second object and is absorbed by the second object, it becomes the internal energy of second object. Heat is the energy in transit. When the energy moves from first body to the second body due to the temperature difference, that energy that flows is called heat. Now, Q represents heat given. So every time I say Q, the symbol Q represents heat given. So if heat is given to the system, we say that Q is positive. And if heat is extracted from the system, then we say that Q is negative. So if you have got two bodies, one at high temperature and one at low temperature, the heat flows from first body to second body, and let's say the amount of heat that flows is 10 joule. So you will say the heat given to this first body equals to minus 10 joule. Why minus 10? Because you are not giving heat, you are extracting heat, equals to 10 joule. So heat given to first body will be minus 10 joule, and the heat given to second body will be equals to plus 10 joule. So beta, remember that when heat is given, it is taken as positive. When heat is extracted from the system, it is taken as negative. Also, both in physics as well as chemistry, this sign convention works. It is same. Whenever heat is given to the system, it is taken as positive. When heat is extracted from the system, it is taken as negative, both in physics as well as chemistry. Now let's talk about next term we need to focus upon, that is internal energy. So what is internal energy? Towards the end of the hour where I taught you KTG, we learned about internal energy. Internal energy is given by F by 2 nRT, where F is the degree of freedom, N is the number of mole, R is the gas constant, and T is the temperature on the Kelvin scale. So we know that the internal energy is given by F by 2 nRT. Now, this internal energy is which type of energy? Kinetic energy, potential energy, both or none. So when we learned the ideal gas postulates, we learned that there is no interaction force between the molecules. As there is no interaction force between the molecules, potential energy is zero. So what we write as the internal energy is nothing but kinetic energy of molecules. It is nothing but kinetic energy of molecules. It can be both translational as well as rotational. For monoatomic molecules, we have got only translational kinetic energy. For diatomic and polyatomic molecules, we get both translational as well as rotational kinetic energy. So again, repeating, what is internal energy? Internal energy for ideal gas is nothing but kinetic energy. Why? Because in the ideal gas postulates, we learned that there is no interaction between the molecules. As there is no force of attraction or repulsion between the molecules, no potential energy exists. So the only type of energy we get is kinetic energy. So for an ideal gas, internal energy is the kinetic energy of gas molecules with respect to the center of mass of gas. So if you have a container and there are multiple gas molecules, so you can find their center of mass. Let's say the center of mass is here. Okay. In the frame of center of mass, what is the net kinetic energy of molecules? That net kinetic energy of molecules is defined as the internal energy. Keep this particular point in mind. Moving on. For monoatomic gas, the degree of freedom is 3. For diatomic gas or polyatomic linear gas, like example C2H2. C2H2 is a polyatomic linear gas, right? Even in this molecule, along the axis, there is no moment of inertia. So again, you get only 2 degree of freedom because of rotation. So for diatomic molecule or polyatomic linear molecule, the degree of freedom is 5. And for polyatomic non-linear molecule, in which you do not have molecules in straight line, for example H2O, you can't find one axis along which moment of inertia will be 0. For polyatomic non-linear molecule, the degree of freedom is 6. So you should remember what is the degree of freedom for different type of molecules. Now beta, since we know that nRT can also be written as PV, so we can write the change in internal energy equals to F by 2 and R delta T. Now, as we know PV equals to nRT, we can write change in PV equals to change in nRT. Usually the number of moles and the gas constant do not change. So we can write the change in pressure into volume equals to nR into delta T. Hence, delta PV equals to nR delta T. So in place of nR delta T beta, you can even write delta PV. So the change in internal energy of the gas equals to degree of freedom by 2 into nR delta T. That can also be written as F by 2 times delta PV. Now beta, understand that delta PV is not same as P delta V. Delta PV is not same as V delta P. No, delta PV means the change in pressure into volume. So this has to be pressure final into volume final minus pressure initial into volume initial. So nR delta T equals to delta PV, nR delta T equals to delta PV. Delta PV means P final V final minus P initial V initial. Keep this small thing in mind. I will use it many a time in this hour only. So let's move on to the next discussion, that is the discussion of work. Before we talk about what is the definition of work here, let's revise the definition of work that we have learned in work power energy. So we have learned that work done equals to integral force dot displacement. When the angle between force and displacement is acute, the sign of work done is positive, and when the angle between force and displacement is obtuse, then the sign of work done is negative. So if the angle between force and displacement is acute, work done is positive, and when the angle is obtuse, the work done is negative. So you have to know this thing. Now, once you know this, what I am trying to explain here is really important. What is the sign of work done by the gas? What is the sign of work done on the gas? In the last year NEET paper, a question came in chemistry which many students did wrong because of the sign convention. So focus on the sign convention right here. It's super duper easy. So let's say when we have a gas and the gas expands. Now beta, when the gas expands, you need to visualize this with me. What will be the direction of force by the gas on the surrounding? So sir, when the gas expands, the gaseous molecule apply radially outward force on the surrounding. Yes. So when the gas expand, the force by the gas on the surrounding is radially outward, and the displacement of molecules at every place is also radially outward. As at all places when the gas expands, the force and displacement are in same direction, the work done by gas is positive. So when the gas expands, the work done by gas is positive. When the gas expands, what is the sign of work done by the surrounding? Now, visualize a small part of gas in 3D. When the gas expands, the surrounding applies radially inward force. But the gas molecules are moving radially outward as the gas is expanding. So when the gas expands, the force by the surrounding will be radially inward. But the displacement of the molecules will be radially outward. As the displacement and force by the surrounding are in opposite direction, we say that the work done by surrounding will be negative. So when the gas expands, yes, the force by the gas on surrounding will be radially outward and the gas molecules move radially outward. So the sign of the work done by the gas is positive. When the gas expands, the force by the surrounding will be radially inward and the gas molecules expand, so the displacement is radially outward. At all points, the angle between force and displacement is 180 degree, so the work done by the surrounding is negative. So you need to keep this small thing in mind. So work done by gas is positive when the gas expands, and work done by the surrounding on the gas is negative. Similarly, when a gas compresses, the molecule of the gas moves radially inward. Now, what will be the sign of work done by the gas? What will be the sign of work done by the surrounding? So when the gas compresses, the gaseous molecule moves radially inward, right? That's why it compresses. Now, what will be the sign of work done by the gas? The gas will exert force on the surrounding radially outward, and the gas molecules are moving radially inward. So when the gas is compressed, the force by the gas molecules are radially outward while their displacement is radially inward. So the sign of the work done by the gas is negative. So the sign of work done by gas is negative. When the gas is compressed, now let's think of the work done by the surrounding. So gas is being compressed, so the surrounding pushes the gas radially inward, as well as the molecules are moving radially inward. So at all places, the angle between force and displacement is 0. So the work done by the force of the surrounding is positive. So when the gas compresses, the work done by the force of the gas is negative, and the work done by the force of surrounding is positive. So when the gas compresses, work done by gas is negative, while the work done by surrounding comes out to be positive. Now, when we say W in physics, what is the W in physics and what is the symbol W in chemistry? In physics, whenever we say W, it means that work done by the gas. In chemistry, whenever we say the word W, which represents the work done, it represents the work done on the gas. So in physics, we say work, it means that work done by the gas. In chemistry, every time they say work, just work, do not mention work done by the body, work done by the gas, work done by the surrounding. They just say work. In chemistry, it means that work done on the gas. That's why the sign comes out to be opposite. In physics, we say when the gas expands, the work done is positive. In chemistry, they say when the gas expands, the work done is negative. In physics, we say when the gas gets compressed, the work done is negative. In chemistry, they say when the gas compresses, the work done is positive. So this is something you have to keep in mind. To understand it easily, a chemist loves the chemical. A chemist has got greatest focus that the chemical gets sufficient energy for the reaction to initiate. A chemist want the energy of the chemical to increase. So chemists take work done on the gas to be positive. Chemists take work done on the gas to be positive. And physicists want gas to expand and do work on the surrounding so that they can utilize the heat engine. So physicists want work should be done by the gas. Chemists want work to be done on the gas so that the chemist can initiate the reactions. So keep this small thing in mind. Now going on to what is the definition of work done by the gas. So we say work done by the gas, infinitely small work done by the gas equals to pressure multiplied by infinitely small change in volume. So infinitely small work done by the gas equals to pressure times the infinitely small change in volume. dW equals to PdV. Integrating both the sides, we will definitely get the work done equals to integral PdV. As soon as we have seen that work done equals to integral PdV, we can say something. What does integral y dx gives you? Sir, integral y dx gives me the area under the y-x graph. So similarly, integral PdV gives you area under the PV graph. So if the gas expands, work done by gas is positive. Why? Because sir, if the gas expands, dV will be positive and pressure always have to be positive. When the gas expands, dV, the infinitely small change in volume, will be positive. The gas is expanding, so the volume will increase, so the dV has to be positive, and the pressure always have to be positive. So if the gas expands, work done by gas is positive. And if the gas is compressed, then the work done by the gas is negative. You need to keep this simple thing in mind. When you write work in chemistry, you just place a minus sign here, because when we are writing work in chemistry, we are writing work done on the gas. In physics, we are writing work done by the gas. Now, if we think of a PV diagram, and let's say on the PV diagram, we are shown a process, let's say from some point A to some point B. So initially the gas has some pressure and volume at A, and finally it has some pressure and volume at B. So what is the work done by the gas during this process? Since we know that work done equals to integral PdV, the area under the pressure volume graph gives you the work done. So when the gas goes from state A to state B, work done is nothing but the area under the PV graph. So work done will be shown by this shaded region. The area under the PV graph is the work done by the gas. The area under PV graph is the work done by the gas. A physicist is interested in work done by the gas. So every time physicist says just work or W, it means work done by the gas. Every time chemistry person say W or work done, it means work done on the gas. So let's move on. Now we need to learn something called the first law of thermodynamics. Before I explain this law, let's take up some simple example. I know that you are a student of science and you know the basic idea of energy conservation. So let's say we have some gas, okay? If let's say a heat equals to 100 joule is given to the gas. So we have given a heat of 100 joule. And this gas expands. When the gas expands, the gas does the work on the surrounding. So when this gas expands, it does some work on surrounding, and the work done by gas on surrounding is 40 joule. So you gave 100 joule of heat to the gas, and the gas expanded and did a work of 40 joule on the surrounding. Okay, what will happen to the internal energy of the gas? Will it increase? Will it decrease? Or will it remain same? So you will say, sir, there is something called principle of conservation of energy. Energy can neither be created nor destroyed. It can only be converted from one form to another. We are providing a heat of 100 joule. Out of the 100 joule, 40 joule has been utilized to do the work on the surrounding. Yes. So what has to happen with the internal energy? Sir, my question is, where is the rest of 60 joule went? You gave 100 joule. Out of 100 joule, 40 joule has been used to do work on surrounding. Where is the rest 60 joule? So that 60 joule is utilized to increase the internal energy. So you will say internal energy of this gas will increase by 60 joule. So we can say the heat given to gas equals to the change in internal energy of the gas plus the work done by the gas. What have we used here? We have used essentially the principle of conservation of energy. Let's take one more example. Let's say you have the gas and you have given 200 joule of heat to the gas. You have given heat, not extracted heat, given heat, as well as the surrounding compresses the gas. And when the surrounding compresses the gas, the surrounding do a work of 80 joule on the gas. So now what will be the change in internal energy of the gas? Sir, from principle of conservation of energy, energy can neither be created nor destroyed. It can only be converted from one form to another. We have given a heat of 200 joule. We are also doing work of 80 joule. Both the energies are going into the gas. This means that, sir, the internal energy of gas should increase by 280 joule. Yes. Now here, what will you write? W. Sir, in physics, whenever we say W, it means work done by the gas. Here the W you have given is work done on the gas. So you will say, sir, actually W should be written as minus 80 joule because work done by the gas is minus 80 joule. So again, heat given to the gas 200 equals to change in internal energy of the gas 280 plus work done by the gas, which is minus 80. What I gave in the question was work done on the gas to be 80 joule. So the work done by the gas will be minus 80 joule, and see the equation balances. So what is first law? Sir, first law is essentially nothing but principle of conservation of energy. So from the principle of conservation of energy, we say that if a heat Q is given to the system, then the heat given Q is equals to change in internal energy of the system plus work done by the system. Q equals to delta U plus W. But in the world of physics, whenever we define something, we define it for infinitely small. Rather than writing Q equals to delta U plus W, what we write is dQ equals to du plus dW in the differential format. The infinitely small heat given equals to the infinitely small change in internal energy plus the infinitely small work done by the gas, and I'm going to use it many a time. Okay, so keep this in mind. Now let's take some example based on first law. Simple example. The first example, if 100 joule of heat is provided to system, 100 joule of heat is provided to system, and internal energy increases by 20 joule, what will be the work done by the gas? So sir, you are providing 100 joule, out of 100 joule, 20 joule has been used to increase the internal energy. Yes. So what happens to the rest 80 joule? The rest 80 joule would have been utilized by the gas in doing work on the surrounding. So the gas must have expanded in this case. I can say with 100% guarantee, if this is the case, then the gas must be expanding. Why? Because the gas is doing work on the surrounding. The gas is doing 80 joule of the work on surrounding, and if gas does work on surrounding, the gas must expand. Hence, we can say that it means that the system must have done 80 joule of work on the surrounding, and to do work on the surrounding, the gas must expand. Let's see next example. If a system does 20 joule of work on the surrounding and its internal energy decreases by 30 joule. So system has done 20 joule of work on surrounding and its internal energy has decreased by 30 joule. What must be the heat given to the system? So there is a system, it has done 20 joule of work on the surrounding. So because of doing 20 joule of work, the internal energy should decrease by 20. But in the question they are saying internal energy decreases by 30. So you are doing, the gas is doing 20 joule of work on surrounding and its internal energy decreases by 30. What can I say about heat? So we say here the system does 20 joule of work on surrounding and the internal energy decreases by 30. It means that 10 joule of heat must have been discarded by the system. If the system do 20 joule of work on surrounding and discard 10 joule of heat to the surrounding, then only the internal energy will decrease by 30 joule. Or you can write the equation. You know that Q equals to delta U plus W. Yes. So The system does 20 joule of work on surrounding. So beta W is equals to 20. Now, and its internal energy decreases by 30 joule. Internal energy decreases by 30. So delta U will be minus 30. So you'll write Q equals to minus 30 plus 20. So Q comes out to be minus 10 joule. Minus sign tells us that this gas rejects 10 joule of energy. So 10 joule of heat must have been discarded by the system. Let's move on. Now let's talk about state function and path function. What is state function? Which depends only on the initial and final state. What is path function? The quantity which depend upon the choice of path. To understand, let's say we have got this PV graph. On this PV graph, there are two states, state A and state B. And we go from state A to state B via two paths. Let's call them path 1 and path 2. Now going from A to B via two paths, which quantity out of the work done, heat given and change in internal energy will be same for both, and which quantity will be different? So let's see. First, let's talk about the work done. If the gas goes from state A to state B, will the work done in both the cases be same? We know that the work done is given by the area under the PV graph. For the process 1, the work done will be equal to the area under the curve 1. For the process 2, the work done will be area under the curve 2. So, following two processes 1 and 2, the work done in the case 1 is more than the work done in case 2. Since the work done by the gas depends upon the choice of path, the work done is a path function. It does not depend only on the initial and final state. It also depends upon the path. That's why work done is a path function. Now let's talk about change in internal energy. We know that change in internal energy can be written as F by 2 nR delta T or F by 2 delta PV. Now this delta PV is what? Delta PV is a P final V final minus P initial V initial. So as delta PV is same for both processes, the final pressure into final volume minus initial pressure into initial volume is same for both the processes. Hence bachon, delta PV is same for both the processes. As delta PV is same, you will say that the change in internal energy which is equal to F by 2 delta PV will be same for both the processes. So hence the change in internal energy in process 1 equals to the change in internal energy in process 2. As the change in internal energy in both the processes is same, we say that the change in internal energy do not depend upon the choice of path. It depends upon only the initial state and the final state. Hence, change in internal energy is a state function. So work done is a path function, change in internal energy is a state function. Now what about the heat given? We know that heat given equals to change in internal energy plus work done. We can say the change in internal energy is same for both the cases, while the work done is greater for the case 1 than case 2. So the change in internal energy is same for both the cases, while the work done is different for both the cases. If you think of the heat given will be higher in which case? So sir, delta U is same. The work done in case 1 is more than the work done in case 2. So delta U is same in both the cases, but the work done in first case is more. So when we find the heat given, which is equals to change in internal energy plus work done, the heat given for first process has to be more than the heat given for second process. So as the work done in first process is more than the work done in second process, we can say that the heat given in first process is more than the heat given in second process. As the heat given to the gas is different for both the processes, we can't say that heat is a state function. It solely do not depend upon the initial and final state. Hence we say heat is a path function. So remember that work done, path function. Change in internal energy is a state function. As the heat given depends upon both change in internal energy plus the work done. Since the change in internal energy is same, it's okay. But the work done is different for different path. Hence, we get that the heat given is different for different paths. Hence, heat given is a path function. It depends upon the path. So this is one small thing that you have to keep in mind. So moving on to a question. The question goes like, there is a gas which is going from state A to state B. Your mission is to find the heat given, the change in internal energy and the work done. So for the monoatomic gas, degree of freedom is 3. Goes from a state A to a state B. Find the work done by the gas, the change in internal energy of the gas and the heat given to the gas. So let's do all the 3 parts slowly. Looking at this graph, how can you find the work done? Sir, the area under PV graph gives the work done. Yes. So all you need to do is to find this area, to find the work done by the gas. So you'll say work done by the gas is nothing but the area of this trapezium. And the area of trapezium can be written as half into sum of parallel side, that is P0 plus 2P0, multiplied by the separation between these 2 parallel sides, that will be 2V0 minus V0, which is V0. So work done equals to area under PV graph, which will be equals to half into sum of parallel side P0 plus 2P0 multiplied by the gap between them, which is 2V0 minus V0, which is V0. So this will be the work done. So half into 3P0 into V0. So the work done comes out to be 3P0 V0 by 2. This is the work done. Now, what is the change in internal energy? We know that the change in internal energy can be written as F by 2 and R delta T, or the change in internal energy can be written as F by 2 delta PV, right? So the change in internal energy equals to F by 2 and R delta T, which is equals to F by 2 delta PV. When I say delta PV, what is the meaning of delta PV? P final V final minus P initial V initial. The P final V final will be 2P0 into 2V0 minus P initial V initial, which is P0 plus V0. So 3 by 2 degree of freedom 3 for monoatomic by 2 into P final V final minus P initial V initial. P final V final will be 4 P0 V0, P initial V initial will be P0 V0. So that will be 3 by 2 into P final V final 4 P0 V0 minus P initial V initial P0 V0. So 4 minus 1 becomes 3 P0 V0. So you get the change in internal energy to be 3 by 2 times 3 P0 V0, which comes out to be 9 P0 V0 by 2. Till now you found anything tough? Now bachon, once you have calculated the work done in the process and you know the change in internal energy in the process, then what has to be heat given? Heat given has to be nothing but the change in internal energy plus work done. So we know that heat given equals to change in internal energy plus work done. You have found the change in internal energy of gas 9 P0 V0 by 2. You have found the work done by the gas 3 P0 V0 by 2. So beta, the heat given has to be equals to 9 P0 V0 by 2 plus 3 P0 V0 by 2. That comes out to be 12 P0 V0 by 2, which is nothing but 6 P0 V0. So this is how you can find all 3: the work done by the gas, the change in internal energy of the gas, as well as the heat given to the gas. So now let's move on. To convert 1 gram of water at 100 degrees centigrade to 1 gram of steam at 100 degrees centigrade. In calorimetry, we have learned that 540 calorie of heat is to be provided. To convert 1 gram of water at 100 to 1 gram of steam at 100, 540 calorie of heat is to be provided. Question is, the change in internal energy is more than, less than, or equal to 540 calorie. So there is 1 gram of water at 100 degrees centigrade. You need to provide it a heat equals to 540 calorie. And then this 1 gram of water converts into steam. So question is, the change in internal energy will be more than 540, less than 540, or equal to 540? Simple question. Now many of students mark the answer as equal to 540, and their argument is, sir, see, we have provided heat equals to 540, so the internal energy should increase by 540, but they forget about the work done. Here we know that when water converts into steam, it expands. When the system expands, it does work on the surrounding. So if we have got water of 1 gram and it converts into steam, it expands, right? So when 1 gram of water at 100 degrees centigrade converts to water vapor, it expands. Now when the water expands, the sign of the work done by H2O will be positive. Work done equals to positive because it expands. Now from first law, Q equals to delta U plus W. Yes sir. Delta U is what we need to find, the change in the internal energy. So we can write delta U equals to Q minus W. The heat given is 540. And from this 540, you have to subtract a positive work. A positive work. So you can say that the change in internal energy will be 540 minus something positive. 540 minus something positive will give you a number less than 540. That's why when 1 gram of water at 100 degrees centigrade is converted to 1 gram of steam at 100, it expands, it does some work on the surrounding. Since it does some work on the surrounding, on out of the 540 calorie provided to it, some part is used in doing work on surrounding, so the change in internal energy has to be less than 540. So we say, as this Q is 540 and this W is some positive work, so the change in internal energy comes out to be less than 540 calorie. So all the heat provided is not utilized to increase the internal energy. Some part of it is used to do the work on surrounding. That's why the internal energy increases by an amount less than 540. They can ask you the same type of question when ice converts to water. So let's see. We know that 80 calorie of heat is to be provided to convert 1 gram of ice to 1 gram of water at 0 degrees centigrade. The change in internal energy is more than 80 calorie, less than 80 calorie, or 0. So the change in internal energy will be more than 80 calorie, less than 80 calorie, or equal to 0. Bacho, tell me, when ice converts to water, what happens to it? It expands or shrinks. We know that ice is lighter than water. That's why ice floats on water, because ice has got less density than water. Since ice has got less density than water, when ice converts to water, it shrinks. It shrinks means that the surrounding does some work on it. Surrounding compresses it. So surrounding does some work on the system when ice converts into water, because when ice converts into water, it shrinks. As well as you are providing a heat of 80 calorie. So you are providing heat of 80 calorie as well as surrounding is doing work on it. I can say with 100% guarantee the change in internal energy has to be more than 80, because you are providing heat of 80 and the surrounding is also doing the work. So the internal energy will increase more than 80 calorie. But how to get it from first law? We know that the heat given equals to change in internal energy plus work done. When ice converts to water, its volume decreases, yeah, it shrinks. That's why water is denser than ice. Hence, we can say work done by the ice is negative. Work done by the surrounding is positive. Work done by the ice is negative. When a system compresses, work done by the system is negative. Think using dW equals to PdV. If the volume decreases, the infinitely small change in volume is negative. Hence, beta, work done is negative. So work done is negative. And you can write delta U, the change in internal energy, equals to Q minus W. Here, your Q is 80. And this W is some negative number. So negative of negative becomes positive. Hence, we can say as W is negative, the change in internal energy will be more than 80. Here you will substitute 80. Here you will substitute something negative. Negative of negative becomes positive. Hence, the change in internal energy comes out to be more than 80 calories. Simple question, important question. Let's move on. Now, we will talk about different type of processes. The first process I'm going to talk about is my personal favorite, isochoric process. So what is isochoric process, which is sometimes also called isometric process? Isochoric process is the process in which the volume remains constant. In an isochoric process, the volume of the gas is constant. If the volume of the gas is constant, from PV equals to nRT, volume constant, number of mole constant, R constant. So you can say the pressure of the gas is directly proportional to temperature of the gas for an isochoric process, which is sometimes also called isometric process. So if we think of the PV graph for an isochoric process, sir, isochoric process, volume is constant, yes. So the volume won't change, okay. Volume won't change. So the volume won't increase or the volume won't decrease. The volume has to remain constant. So what does the graph of isochoric process looks like on a PV diagram? Volume has to be constant. So think of a line on which the volume is constant. Volume neither increases nor decreases. Volume is constant. So let's say gas goes from state A to state B. In this case, you will say the volume of the gas is constant. But as we can see, the pressure of the gas is increasing. And from PV equals to nRT, V is constant N is constant, R is constant. Going from state A to state B, pressure is increasing, so the temperature of the gas must be increasing. So we can say increasing pressure and constant volume. So this process represents a process in which the volume is constant. Volume is constant, but the pressure is increasing, and hence the temperature will also be increasing. What does the isochoric process looks like on a VT diagram? So sir, VT diagram, volume temperature diagram. Again, the volume has to be constant. So if you think of 2 points on a graph of isochoric process on VT, you will say, sir, the volume has to be constant. So this is what the graph looks like, a straight line. Here, the process represents a process in which volume is constant and temperature increases. So increasing temperature at constant volume. What does the constant volume process looks like on a PT diagram? So sir, we know that PV equals to nRT, volume is constant, N is constant, R is constant, so pressure is directly proportional to temperature. So what we get is a straight line passing through the origin. So this is what the graph looks like on a PT diagram. So as PV equals to nRT, for constant volume you can say pressure is directly proportional to temperature. So this is constant volume processes shown on different curves. Now let's move on and understand what is the work done in an isochoric process. We know that work done equals to integral PdV. Yes sir. In the isochoric process, the volume remains constant. Yes. If the volume remains constant, the infinitely small change in volume will be zero. Volume is not changing, so the infinitely small change in volume will be zero. As the infinitely small change in volume is zero, the work done by the gas in an isochoric process has to be zero. So as in isochoric process, the infinitely small change in volume is zero, so the work done by the gas is zero. I have already told you, when the gas expands, work done by gas is positive. When the gas contracts, work done by gas is negative. If the volume of the gas does not change, what will be the sign of work done by the gas? There is no work being done by the gas. So the work done by the gas at constant volume has to be zero. So the work done will be zero. Now let's talk about other things for isochoric process. So we know that the change in internal energy is given by F by 2 nR delta T. And the change in internal energy can also be written as F by 2 delta PV. Now better think of an isochoric process. What is delta PV? So delta PV means P final V final minus P initial V initial. For an isochoric process, the volume remains constant. Yes. Since the volume remains constant, the final volume has to be same as initial volume, and let's say this volume equals to V. So if in place of final volume and initial volume I substitute V, what we get is P final into V minus P initial into V. So you get delta PV to be equals to V times P final minus P initial. And P final minus P initial is nothing but delta P. So we can write delta PV for an isochoric process to be equals to V delta P. So as the volume is constant, delta PV can be written as V into P final minus P initial. That becomes equals to V times delta P. So the change in internal energy equals to F by 2 and R delta T, which is same as F by 2 V delta P. Now talking ahead about the heat given. The heat given equals to change in internal energy plus work done. Yes. The work done in an isochoric process is zero. Volume is not changing. So we can say all the heat given to the gas is utilized by the gas to increase its internal energy. All the heat given to the gas is utilized by the gas to increase its internal energy. So heat given equals to F by 2 nR delta T plus 0. In place of delta U, you can write F by 2 nR delta T, and in place of work done, you can write 0. So the heat given equals to change in internal energy equals to F by 2 nR delta T. So we can now collect all the important points which we have learned about isochoric process. For an isochoric process, what is the condition? Volume is constant. Then work done by the gas is 0. Next, the heat given equals to change in internal energy equals to F by 2 nR delta T equals to F by 2 V delta P. Moreover, remember this particular statement. All the heat supplied to the gas is utilized to increase the internal energy of the gas. No work is done by the gas. All the heat provided to the gas is utilized by the gas to increase the internal energy. If you have got a gas at constant volume, then on supplying heat, its internal energy will increase. On extracting heat, its internal energy will decrease. Simple. So now let's talk about isobaric process. What is isobaric process? The process in which pressure is constant. So pressure do not change. So if you visualize isobaric process on PV diagram, the pressure should be constant. The pressure should neither increase nor decrease. So let's say this is the process AB showing you isobaric process on the PV diagram. So here you can see pressure is constant, but on going from A to B, the volume is increasing. So volume increases, but the pressure is constant. If you think of the same process on PT diagram, pressure temperature diagram, again the pressure has to be constant as the temperature increases. So this particular process shows an isobaric process in which temperature is increasing. So pressure is constant and temperature is increasing. If you draw the isobaric process on the VT diagram, so you know that PV equals to nRT, yes sir. For isobaric process, pressure is constant, N is constant, R is constant, so the volume is directly proportional to temperature. So on the VT diagram, you get a straight line passing through the origin, and you can say from PV equals to nRT, as P is constant, the volume is directly proportional to temperature for an isobaric process. So now more on isobaric process. Isobaric process is the one in which pressure is constant. Yes sir. Now we know that work done equals to integral PdV. You can take the pressure outside the integration only when pressure is constant, which it is for isobaric process. So as the pressure is constant, you can take it out of the integration and write work done equals to P times integral dV from initial volume Vi to final volume Vf. Integral dV gives you what bacho? V. Lower limit is Vi, upper limit is Vf. So you will write V final minus V initial, which is nothing but delta V. So you can write work done equals to P delta V. For which process? For isobaric process. Now you know that PV equals to nRT. Yes sir. So we can even write delta PV equals to nR delta T. Yes sir. Since delta PV equals to nR delta T. So we get for isobaric process, as P is constant, we can write delta PV to be equals to delta PV is P final V final minus P initial V initial, and pressure is constant. So take the final pressure equals to initial pressure equals to P. So you will get PV final minus PV initial. That is P times delta V. So delta PV comes out to be equals to P times V final minus V initial, which is P delta V. So remember, for an isobaric process, delta PV equals to P delta V as the pressure is constant, and delta PV equals to nR delta T. Hence we can write the work done equals to P delta V equals to nR delta T. So for an isobaric process, the work done by the gas equals to nR delta T, or that can be written as P delta V. Both are equally good. So if you just know the number of moles of gas and the rise in temperature of gas, you can tell what is the work done by the gas in the isobaric process. Now what about the change in internal energy? The change in internal energy is given by F by 2 nR delta T. For an isobaric process, nR delta T is same as P delta V. So the change in internal energy can be written as F by 2 nR delta T or equal to F by 2 P delta V. Because for an isobaric process, delta PV, the change in pressure into volume, is same as P delta V. So this is the second thing. Now what about the heat given? We know that heat given equals to change in internal energy plus work done. The change in internal energy is F by 2 nR delta T. The work done is nR delta T. So you can write F by 2 nR delta T plus nR delta T. If you take nR delta T common, you get F by 2 plus 1 nR delta T. Or in place of nR delta T, you can write P delta V. So if you take P delta V or nR delta T common, you will write the heat given as F by 2 plus 1 nR delta T, which is same as F by 2 plus 1 P delta V. So this is something you need to remember for the heat given. Now I will make you remember all this, just stay focused. So now you can say for an isobaric process, pressure is constant, yes sir. Work done equals to nR delta T or P delta V. The change in internal energy can be written as F by 2 nR delta T or F by 2 P delta V, because for an isobaric process, delta PV, which is same as nR delta T, is same as P delta V. So this is the change in internal energy. How to write the heat given? Heat given equals to change in internal energy plus work done. So if you add nR delta T with F by 2 nR delta T and then take nR delta T common, you can write heat given as F by 2 plus 1 into nR delta T. Or in place of nR delta T, you can write P delta V for an isobaric process. So you will write F by 2 plus 1 into P delta V. Now there is a ratio for work done is to change in internal energy is to heat given. You can see that work done is nR delta T. The change in internal energy is F by 2 nR delta T. And the heat given is F by 2 plus 1 nR delta T. So you can say the ratio of work done is to change in internal energy is to heat given. Work done is to change in internal energy is to heat given equals to nR delta T is to F by 2 nR delta T is to F by 2 plus 1 into nR delta T. Cancel out bachcho, nR delta T. So you get 1 is to F by 2 is to F by 2 plus 1. This is the ratio of work done to the change in internal energy to the heat given for an isobaric process. So you get ratio of work done is to change in internal energy is to heat given to be equals to 1 is to F by 2 is to F by 2 plus 1. And beta, this is the number 1 FAQ in previous year paper. They will give you one of them, either work done or heat given or the change in internal energy, and they will ask you the other two for an isobaric process. We will practice this type of question, but before that, let's understand here a little bit more. We know that the work done is to change in internal energy is to heat given has the ratio 1 is to F by 2 is to F by 2 plus 1. Now for different type of gases, what will be the ratio? For monoatomic gas, the degree of freedom is 3. So you will say for monoatomic gas, the ratio will be 1 is to 3 by 2 is to 3 by 2 plus 1, that is 5 by 2. For a diatomic gas, the degree of freedom will be substituted as 5. So you will get 1 is to 5 by 2 is to 5 by 2 plus 1, that will be 7 by 2. So you get 1 is to 5 by 2 is to 7 by 2. For a polyatomic non-linear gas, the degree of freedom is 6. So you will get 1 is to 6 by 2, which is 3, is to 6 by 2 plus 1, that is 3 plus 1, that is 4. So for polyatomic gas, the ratio comes out to be 1 is to 3 is to 4. Now, to increase the temperature by same amount, that is to increase the internal energy by same amount, in the case of isobaric process, the heat provided has to be more. So more heat should be provided in the case of isobaric process compared to isochoric process. Why? In the isochoric process, the volume is constant. Yes. All the heat provided to gas is utilized in increasing its internal energy. The work done by the gas is 0 for isochoric process. But for isobaric process, where the pressure is constant, on providing the heat, some part of the heat is utilized in increasing internal energy, while some part of the heat is utilized in doing work on the surrounding. So the part of heat provided utilized in increasing the internal energy is less. That's why more heat has to be provided. So remember that more heat should be provided in case of isobaric process to increase the internal energy by the same amount, because in case of isobaric process, some part of the heat supplied is utilized in doing work on the surrounding. So before we move on, let's practice some question based on this. So the question, if the heat provided to diatomic gas in isobaric expansion is 350 joule, heat provided is 350 joule. What is the work done and what is the change in internal energy? The type of gas given to us is diatomic. For diatomic gas, the degree of freedom is 5. So we know that for a gas undergoing isobaric process, the work done to the change in internal energy to the heat given is in the ratio 1 is to F by 2 is to F by 2 plus 1. For diatomic gas, you will substitute Fs5. So you will get 1 is to 5 by 2 is to 5 by 2 plus 1. That becomes 7 by 2. They have given me in the question what is the heat given. They have given me Q to be 350. And they are asking me what is the work done and what is the change in internal energy. I can easily find it because I know the ratio between them. So we can say this ratio, if I multiply 2 to each term, comes out to be 2 is to 5 is to 7. 5 by 2 into 2 becomes 5. 7 by 2 into 2 becomes 7. So the heat given upon change in internal energy, heat given upon change in internal energy has to be 7 by 5. Now heat given is given as 350. Our mission is to find the change in internal energy. So we can write 350 by delta U equals to 7 by 5, or cancelling out here you get a 50. So delta U equals to 50 into 5. That comes out to be 250 joule. Now once you know that heat given is 350 and the change in internal energy is 250, you can even use Q equals to delta U plus W to find the work done. Substitute this as 350, delta U as 250. You will get the work done to be 100. Or you can again use the ratio. You can say Q by W has to be 7 by 2. Now you know that Q is 350. So you get 350 by work done equals to 7 by 2. Again cancel out. Here you get a 50. So the work done comes out to be 100 joule. These type of questions are FAQ. Frequently asked out question in previous year paper. So let's practice one more question of same type. Question is, the change in internal energy of a monoatomic gas. The change in internal energy of a monoatomic gas undergoing isobaric process is 60 joule. So the change in internal energy is given. They are asking me what is the work done, what is the heat given. So we know that for an isobaric process, the work done is to change in internal energy is to the heat given is in the ratio 1 is to F by 2 is to F by 2 plus 1. For monoatomic gas, we will substitute the degree of freedom to be 3. So you get 1 is to 3 by 2 is to 3 by 2 plus 1, that is 5 by 2. Now you know what is the change in internal energy. So delta U is given and they are asking you W and Q. So you can say bachcho, W by delta U, the work done upon change in internal energy equals to 1 is to 3 by 2. That becomes 2 by 3. So once you know that the work done upon change in internal energy equals to 2 by 3 and they have given you what is the change in internal energy, you can find out work done. So you write work done upon 60, which is given in the question, equals to 2 by 3. Cancel this out, here you get a 20. So the work done comes out to be simply 40 joule. Now the next part, what is the heat given? Now once you know that change in internal energy is 60 and the work done is 40, from Q equals to delta U plus W, you can write it as 60 plus 40, that becomes 100 joule. But if you need to find the heat given using the ratio, that can be done as well. You will write delta U upon heat given equals to 3 by 2 upon 5 by 2, which is nothing but 3 by 5. So you will write delta U by Q equals to 3 by 5. In place of delta U, you can write 60 given in the question. So 60 upon the heat given equals to 3 by 5. Cancelling out 3, here you get 20. So the heat given comes out to be 20 into 5, which is 100 joule. So again, I am saying these type of questions are simple question and they come in competitive examination every year. So this is a FAQ. Let's move on. So now the process we will talk about is isothermal process. The name itself says isothermal, temperature is constant. So in an isothermal process, temperature is constant. From PV equals to nRT. If temperature becomes constant, the whole right hand side becomes constant. So the isothermal process can also be represented as PV equals to constant. So if you think of an isothermal process on the PT diagram, temperature has to be constant. So temperature has to be constant. So you will get a straight line like this. Temperature won't increase, won't decrease. Temperature has to be constant. So let's say we have a process like this going from A to B. This is an isothermal process on the PT diagram. In this process, you can see the pressure is increasing going from A to B. Yes. Temperature is constant. Pressure is increasing. What can we say about volume? Sir, from PV equals to nRT. For a constant temperature process, the right hand side will be constant. So if the pressure increases going from A to B, then the volume should decrease. So from PV equals to nRT, as PV equals to constant, from A to B, the pressure increases. B has got higher pressure than A. So B will have lower volume than A and the volume decreases. Similarly, if you draw a constant temperature process, an isothermal process on the VT diagram, then again the temperature has to be constant. Let's say you see a process going from A to B, isothermal process on a VT diagram. What can you say looking at this process? You will say, sir, going from A to B, the volume is increasing. So from A to B, as the volume increases, the pressure should decrease. Why? Sir, PV equals to nRT. Right hand side is constant. Going from A to B, if the volume increases, the pressure should decrease now, because their multiplication has to be constant. Moving on, what does an isothermal process looks like on a PV diagram? So sir, on a PV diagram, we have learned that this looks like an isotherm, a rectangular hyperbola. So you will say PV equals to constant, yes. So pressure is inversely proportional to volume, yes. On the y-axis you have pressure, on the x-axis you have got volume. If y is proportional to 1 by x, the type of curve you get has a special name. It's rectangular hyperbola, and this particular shape will be it. Okay. Now, area under the PV graph gives you what? The work done. But this work you can see is not easy to calculate because there is a curved part involved, and this curve is not part of a circle. It is a part of hyperbola. So how to find the work done for an isothermal process? Let's see. So for isothermal process, we know that PV diagram, we get an hyperbola. We can say that the P initial V initial has to be equals to P final V final. Why, sir? PV equals to constant now. So the initial pressure into initial volume has to be equals to final pressure into final volume. So P initial V initial equals to P final into V final. For an isothermal process, you can say PV, the pressure times volume at any given position on this curve, has to be equals to nRT, has to be equals to constant. So P initial V initial equals to P final V final equals to the multiplication of pressure into volume at any position in this process equals to nRT, because this process takes place at a constant temperature. nRT equals to constant. So this is the equation for an isothermal process. Now how to find the work done? We know that the work done equals to integral P dV. For an isochoric process, I said dV is 0, so the work done is 0. For an isobaric process, I said pressure is constant, so we can take it out of the integration. But in isothermal process, as the volume changes, the pressure also changes. As the volume increases, the pressure decreases. So pressure is not at all constant, we can't take it out of integration. So what to do? From PV equals to nRT, you can substitute in place of P nRT by V. So you can write work done equals to integral nRT by V in place of P into dV. Now since nRT is constant, you can pull it out of the integration. So what you get is work done equals to nRT integral dV by V. Integral dx by x is bachcho ln x. Similarly, integral dV by V gives you ln V. Lower limit Vi, upper limit Vf. So you will write work done as nRT, which is constant outside. Integration of dV by V. Integration of dV by V gives you ln V. Lower limit is Vi, upper limit is Vf. Always substitute upper limit ln Vf minus lower limit ln Vi. Now ln A minus ln B can be written as ln of A by B. So you can write ln final volume minus ln initial volume as ln of final by initial. So the work done comes out to be nRT ln V final by V initial. Now there are many different ways to write the work done for isothermal process. Why, sir? In place of nRT, I can write PV, I can write P initial, V initial, I can write P final, V final. In place of Vf by Vi, V final by V initial, I can even write V final by V initial, I can even write P initial by P final. So there are many different ways to write the same equation. So here we have been given nRT ln V final by V initial. The same thing can also be written as, in terms of pressure, as nRT ln P initial by P final, because we know that V final by V initial is same as P initial by P final. Or in place of nRT, we can write Pi Vi, and we will write work done as Pi Vi ln V final by V initial. Or in place of Pi Vi, we can substitute and write Pf Vf V final by V initial. Or in place of V final by V initial, in this equation we can write P initial by P final. Or in place of V final by V initial, in this equation we can write P initial by P final. All of them are one and the same thing, and all of them are different ways to write the same equation. So sir, what should I remember? First, for an isothermal process, temperature is constant. Then you have to remember this thing: P initial V initial equals to P final, V final equals to PV equals to nRT, and all of this is constant. And the work done equals to nRT ln V final by V initial. And then you can write all these other ways of writing the same work. To understand this work, let's practice a question before we move on about isothermal process. The volume of 2 liter of gas under atmospheric pressure increases to 4 liter isothermally. Determine the work done by the gas. So there is 2 liter of gas under atmospheric pressure. Its volume increases to 4 liter isothermally. So initially you have got 2 liter of gas under atmospheric pressure, and its volume increases to 4 liter isothermally. Determine the work done by the gas. So first of all, you should know that liter is not SI unit, and atmospheric pressure is also not SI unit of pressure. So you should know how to convert from liter the volume into meter cube. So the conversion goes like 1 liter is equals to 10 raised to power of minus 3 meter cube. Personally, I think of it this way: 1 meter cube equals to 1000 liter. 1 meter cube equals to 1000 liter. If you have a cubical tank of dimension 1 meter by 1 meter by 1 meter, its volume will be L into B into H, 1 into 1 into 1 meter cube. In this tank, you can place 1000 liter of water. So 1 meter cube is equal to 1000 liter. Or 1 liter equals to 10 raised to power of minus 3 meter cube. Both are one and the same thing. Similarly, 1 atm equals to nearly equal to 10 raised to power of 5 Pascal. Now our mission is to write the work done. We can write work done as P initial V initial into ln V final by V initial. In place of P initial, substitute 10 raised to power of 5 Pascal. In place of V initial, substitute 2 liter, that will be 2 into 10 raised to power of minus 3. Ln V final by V initial, that is 4 by 2. So what you get here is work done equals to 1 into 10 raised to power of 5 P initial into V initial. 2 liter is the initial volume, that will be written as 2 into 10 raised to power of minus 3 meter cube. Ln V final by V initial, the final volume is 4 into 10 raised to power of minus 3 meter cube upon initial volume, which is 2 into 10 raised to power of minus 3 meter cube. So this get cancelled. So what you get is here 10 raised to power of 5 into 10 raised to power of minus 3 gives you 10 raised to power of 2. So you get 2 into 10 raised to power of 2, 2 into 10 raised to power of 2 ln 4 by 2, which is ln 2, and ln 2 is 0.693. so you can further solve 2 into 10 square into 0.693 if you wish to. Otherwise, move on. So now let's keep on learning about isothermal process. So how do you write the change in internal energy for an isothermal process? Sir, the change in internal energy for any process is given by F by 2 nR delta T. Yes. The question is, what is the change in temperature in an isothermal process? Sir, there is no change in temperature. As there is no change in temperature, the change in internal energy in case of an isothermal process is 0. So change in internal energy is given by F by 2 nR delta T. As the temperature is constant, the change in temperature becomes 0. As the change in temperature becomes 0, so the change in internal energy is 0. So remember, for an isothermal process, temperature is constant, so the change in temperature is 0, hence the change in internal energy, which is written as F by 2 and R delta T, has to be equal to 0. So no change in internal energy of the gas takes place. Moving on. Heat given has to be equals to change in internal energy plus work done. Yes, sir. In case of isothermal process, the change in internal energy is 0. Hence, you can say all the heat supplied to the gas is utilized by the gas to do work on the surrounding. The gas stores nothing. So if you have a gas and you provide it 100 joule of heat such that the temperature remains constant, then the gas will use this entire 100 joule to do the work on the surrounding, and there will be no change in the internal energy of the gas. So Q equals to 0, and in place of work done you can write nRT ln V final by V initial, or you can write P initial V initial ln V final by V initial. So now in the nutshell, all the points about isothermal process. First, for an isothermal process, temperature is constant. So you can even write it as PV equals to constant. So P initial V initial equals to P final V final. The change in internal energy in the case of isothermal process is 0, because change in internal energy is F by 2 nR delta T. As the change in temperature is 0, the change in internal energy comes out to be 0. Next point, bachcho. The heat given equals to work done for an isothermal process. The heat given equals to change in internal energy plus work done. But for an isothermal process, the change in internal energy becomes 0. Hence, the heat given equals to work done. Next, the heat given equals to work done equals to nRT ln V final by V initial. In place of nRT, you can even write P initial V initial. So this can also be written as P initial V initial ln V final by V initial. There are many more ways to write the same work done, which will be equal to heat given. In place of nRT, you can even write P final V final. In place of V final by V initial, you can write P initial by P final. I'm not at all writing all of them here. That will just waste up the whole space. Next thing. Which important statement has to be remembered for an isothermal process? So, in an isothermal process, all the heat provided to gas is spent by the gas to do the work on the surrounding without storing anything. So, if you have got a gas which is under isothermal process and you provide some amount of heat, the gas does the same amount of work on the surrounding. It does not increase its internal energy at all. So let's move on to the next thing. So the next process we need to talk about is adiabatic process. So what is an adiabatic process? An adiabatic process is the one in which no heat exchange takes place. So isochoric, constant volume; isobaric, constant pressure; isothermal, constant temperature; adiabatic, no heat exchange. So we know the first law says that the heat given equals to change in internal energy plus work done. For an adiabatic process, the heat given is 0. So from dq equals to du plus dw. For an adiabatic process, this infinitely small heat given is 0. So you write 0 equals to du plus dw. Now you can write du as how? So du can be written as F by 2 nR dt, or can be written as F by 2 differentiation of PV, because you know that PV equals to nRT. So dPV equals to differentiation of nRT, as N and R are constant. You can take them out of the differentiation. So you get dPV equals to nR times dt. So you can write 0 equals to F by 2 dPV. In place of nR dt, you can write dPV plus infinitely small work done, which by definition goes as PdV. Now you need to expand this particular term, PdV. Differentiation of two terms in multiplication is given by differentiation of first term multiplied by second term as it is, plus differentiation of second term multiplied by first term as it is. So you will write this equal to F by 2 into dP into V plus dV into P plus PdV. Taking terms of PdV and PdV on one side and dP into V on the other side, you will get minus F by 2. Take this term to the left hand side, minus F by 2 dP into V equals to F by 2 plus 1 into P dV. Okay. Now from here bring this F by 2 down there and this V down here and this P down here. So we can even write dP by dV equals to F by 2 plus 1 upon F by 2, and the minus sign goes to the right hand side, into P by V. Now this quantity f by 2 plus 1 upon f by 2 will keep on coming in our further calculation. So we have denoted a symbol for it. It's called gamma, which is nothing but Poisson's ratio. What is that? We will talk about it later. So in place of f by 2 plus 1 upon f by 2, we are writing gamma. So f by 2 plus 1 upon f by 2 equals to gamma, let's say. So we can write dp by dv equals to minus gamma p by v. dp by dv equals to minus gamma p by v. Beta, by the way, what is dp by dv? So dp by dv is the slope of PV graph. dp by dv is the slope of PV graph. So dp by dv equals to minus gamma p by v. Now bring this p here and this dv up there. So you will get dp by p equals to minus gamma dv by v. Integrating both the side, integration of dp by p gives you ln p, integrating from p initial to p final, and integration of dv by v gives you ln v, integrating from v initial to v final. Always substitute upper limit minus lower limit. So you get ln p final minus p initial, that is ln p final upon p initial equals to minus gamma times ln v final upon v initial. And once you have got minus gamma ln v final by v initial, you can bring this gamma to power. So this can be written this way as well. Now removing ln from both the side, you get p final by p initial equals to v initial by v final raised to power of gamma. Here we had v final by v initial raised to power of minus gamma. That can be written as v initial by v final raised to power of gamma. Now cross multiplying, you get p final into v final raised to power of gamma equals to p initial v initial raised to power of gamma. So p final v final raised to power of gamma equals to p initial v initial raised to power of gamma. Now what are we doing here? We are trying to find the equation of an adiabatic process. Why? So that we can find out work done. So just remember, for an adiabatic process, P initial V initial raised to power of gamma equals to P final V final raised to power of gamma. So for an adiabatic process, we say that PV raised to power of gamma remains constant. And this is the equation of state for an adiabatic process. PV raised to power of gamma equals to constant. So using it, we can find the work done. So for an adiabatic process, P initial V initial raised to power of gamma equals to P final V final raised to power of gamma equals to PV raised to power of gamma equals to a constant. Now we know that work done equals to integral P dV. In case of isobaric process, pressure was constant, we took it out, right? Here the pressure is not at all constant. The pressure will change with the volume. So here in place of pressure, we substitute C upon V raised to power of gamma and then integrate and then solve, and on solving we get the work done to be equal to P final V final minus P initial V initial upon 1 minus gamma. Keep this particular formula in mind. What is the work done in an adiabatic process? P final V final minus P initial V initial upon 1 minus gamma. P final V final minus P initial V initial upon 1 minus gamma. You can write this P final V final minus P initial V initial also as delta PV, because delta PV is P final V final minus P initial V initial. So in place of P final V final minus P initial V initial, we can even write delta PV. So this work done in an adiabatic process can also be written as delta PV upon 1 minus gamma, and delta PV can also be written as NR delta T. So the work done in an adiabatic process should be remembered as delta PV upon 1 minus gamma or NR delta T upon 1 minus gamma. What is gamma? We will talk about it, do not worry. Now work done can be written as this. Now from first law, we know that the heat given equals to change in internal energy plus work done. For an adiabatic process, the heat given is 0. So for an adiabatic process, you can say the change in internal energy equals to minus times the work done. We know that the work done in an adiabatic process is given by delta PV upon 1 minus gamma, which is same as NR delta T upon 1 minus gamma. So change in internal energy equals to minus times of delta PV upon 1 minus gamma equals to minus times of NR delta T upon 1 minus gamma. The picture is not over. Let's understand more. What is gamma? Sir, gamma is nothing but F by 2 plus 1 upon F by 2. For monoatomic gas, we know that degree of freedom is 3. So the gamma will be 3 by 2 plus 1 upon 3 by 2, 3 by 2 plus 1 upon 3 by 2. That becomes 5 by 2 upon 3 by 2, and 5 by 2 upon 3 by 2 comes out to be 5 by 3. 5 by 3 on calculation comes out to be 1.66 recurring. Similarly, what is the gamma for diatomic gas? For a diatomic gas, you will substitute the degree of freedom as 5. So the gamma will come out to be 5 by 2 plus 1 upon 5 by 2, that is 7 by 2 upon 5 by 2, and that comes out to be 7 by 5, and that will be equal to 7 by 5 will be 1.4. What will be the gamma for a polyatomic gas? For a polyatomic gas, the degree of freedom will be 6. So you will write 6 by 2 plus 1 upon 6 by 2, 6 by 2 plus 1 upon 6 by 2 gives you 3 plus 1 upon 3, that is 4 by 3. And 4 by 3 can be written as 1.33 recurring. So here you can see that the gamma of monoatomic gas is 1.66, the gamma of diatomic gas is 1.4, the gamma of polyatomic gas is 1.33. Hence we can say that gamma mono is greater than gamma dia is greater than gamma poly. Gamma for monoatomic gas is greater than gamma for diatomic gas, and it is greater than gamma for polyatomic gas. Now we can even say here, if I multiply this f by 2, we will write f by 2 into gamma equals to f by 2 plus 1. Yes, sir. If you bring this f by 2 to the left hand side, you will write f by 2 times gamma minus 1 equals to 1. Yes, sir. Or you can write from here f by 2 equals to 1 upon gamma minus 1. And you can bring this 2 up and write the degree of freedom equals to 2 upon gamma minus 1. Now this is the formula which is taught many a time, but I tell students to stick to the basic. What is the definition of gamma? Gamma is nothing f by 2 plus 1 upon f by 2. This is the value which we substituted as gamma when we wish to solve for adiabatic process. So gamma is nothing but f by 2 plus 1 upon f by 2. I recommend you to remember this rather than this formula, that formula. Do not go after many a formula, right? So focus on this one. So now, understanding adiabatic process in the nutshell, what we have learned in the entire adiabatic process. The first thing, the heat given in an adiabatic process is 0. The equation of state is given by PV raised to power of gamma equals to constant, where gamma is nothing but f by 2 plus 1 upon f by 2, where f represents the degree of freedom. For mono, you will take 3. For dia, you will take 5. For polyatomic, you will take 6. Remember that gamma mono greater than gamma dia greater than gamma poly. Moving on, we say for an adiabatic process, the work done, which is same as minus times the change in internal energy. Sir, how do you know? From first law, heat given equals to change in internal energy plus work done. For an adiabatic process, heat given is 0. So the change in internal energy equals to minus times work done, or work done equals to minus times the change in internal energy. So work done equals to minus times the change in internal energy. And this work done can be written as delta PV upon 1 minus gamma, or nr delta T upon 1 minus gamma. So nr delta T upon 1 minus gamma, which is same as delta PV upon 1 minus gamma. Now the last statement, and which is really important. The heat given equals to change in internal energy plus work done. Yes, sir. Now, for an adiabatic process, the heat given is 0. So if you have a gas and you are not at all providing it any heat, and let's say this gas does a work of 20 joule, it expands and does a work of 20 joule on the surrounding. So from where did it get the energy to do a work of 20 joule on the surrounding? So sir, if the gas expands and does a work of 20 joule on the surrounding and you haven't provided any heat, it means that the gas has done work at the cost of its own internal energy. So if a gas undergoes adiabatic expansion, it does the work at the cost of its own internal energy. That's why all the adiabatic expansions are accompanied with cooling, because when the gas expands, you are not supplying any heat. The gas is expanding and doing work on surrounding. It is doing the work on surrounding at the cost of its own internal energy. So its temperature will fall. That's why all adiabatic expansions are accompanied with cooling of gas. So if the gas expands, the work done by gas is at the cost of its internal energy. So adiabatic expansions are accompanied with cooling. So moving on, now we will discuss all the 4 processes one after another, so that it will be a good revision for what we have learned in this hour. So first, let's revise our isochoric process. In isochoric process, volume is constant. Yes, sir. Work done by gas is 0 because there is no volume change. Now, what is the heat given to gas? Sir, the heat given to gas equals to change in internal energy plus work done. For isochoric process, work done is 0. So the change heat given equals to change in internal energy equals to F by 2 and R delta T, which can also be written as F by 2. In place of nR delta T, we can always write delta PV. Delta PV. But for isochoric process, since volume is constant, we can write V times delta P. So V delta P. So heat given equals to change in internal energy equals to F by 2 nR delta T equals to F by 2 times V delta P. In an isochoric process, all the heat supplied to the gas is utilized by gas to increase its internal energy. All the heat supplied to the gas is utilized in increasing the internal energy of the gas. This is the first process we learned. The second process we learned was isobaric process. In an isobaric process, the pressure remains constant. The work done by the gas can be written as nR delta T or P delta V. nR delta T or P delta V. Next thing, bachcho. Here, the change in internal energy of the gas can be written as F by 2 and R delta T. For all processes, the change in internal energy can be written as F by 2 and R delta T. And for isobaric process, since nR delta T can be written as P delta V, the change in internal energy equals to F by 2 and R delta T, which is same as F by 2 times P delta V. The pressure remains constant. The heat given has to be sum of change in internal energy plus work done. So the heat given equals to F by 2 plus 1 and R delta T. Better simply do na, F by 2 and R delta T. The change in internal energy plus the heat given and R delta T. Take and R delta T common. So you get F by 2 plus 1 times and R delta T. Or this can also be written as F by 2 plus 1 times P delta V. Oh, sorry. I meant to write here P delta V. Moving on. Ratio of work done is to change in internal energy is to heat given is in the ratio 1 is to F by 2 is to F by 2 plus 1. So this is for isobaric process. Okay. Now let's revise the next one, the isothermal process. Isothermal process is the one in which temperature remains constant. Since temperature remains constant, PV remains constant. Since temperature do not change, we say that the change in internal energy is 0 because we know that the change in internal energy is given by F by 2 and R delta T. For an isothermal process, delta T becomes 0. So the change in internal energy becomes 0. So from Q equals to delta U plus W, since delta U becomes 0, we can say all the heat given to the gas is utilized by gas in doing work on the surrounding. The heat given equals to work done by the gas. So heat given equals to work done. Now I told you there are many ways to write this work done, but we will focus on just two. So the work done can be written as nRT ln V final by V initial. In place of nRT you can write P initial V initial, and in place of final volume by initial volume you can even write initial pressure upon final pressure. Remember that in the case of isothermal process, all the heat provided to gas is spent by the gas in doing work on the surrounding. All the heat provided to gas is utilized by gas in doing work on the surrounding. The gas stores no part of the heat provided to it to increase the internal energy. This happens in isothermal process. And the last process we have learned till now, the fourth one, which is adiabatic process. For adiabatic process, the heat given is 0. The equation of state is given by PV raised to power of gamma equals to constant, where gamma is bachcho F by 2 plus 1 upon F by 2. F is the degree of freedom. For monoatomic 3, for diatomic 5, for polyatomic 6. Now, when you find out the value of gamma, for monoatomic, the value of gamma comes out to be 5 by 3. For diatomic, substituting F as 5, the value of gamma comes out to be 7 by 5. And for polyatomic, the value of gamma comes out to be 4 by 3. So we get that gamma mono greater than gamma dia greater than gamma poly. Next thing, heat given is 0. So from Q equals to delta U plus W, since the heat given is 0, the change in internal energy equals to minus times the work done, or work done equals to minus times the change in internal energy. So work done equals to minus times the change in internal energy, and this will be equal to Nr delta T upon 1 minus gamma or delta PV upon 1 minus gamma. This will be the work done, which will be equal to minus times the change in internal energy. Now, for an adiabatic process, one need to remember, if the gas expands, the work is done by the gas at the cost of its internal energy. That's why all adiabatic expansions are accompanied with cooling. When the gas expands, it does the work on surrounding at the cost of its internal energy. So if the gas expands, its internal energy decreases, the temperature decreases, and the gas cools down. So now let's talk about molar specific heat. We have already learned specific heat, the amount of heat required to raise the temperature of 1 kg of substance by 1 degree centigrade, right? Now we will talk about molar specific heat, the amount of heat required to raise the temperature of 1 mole of gas by 1 degree centigrade. So rather than talking about 1 kg, now we are talking about 1 mole. So the relationship between heat given and molar specific heat is Q equals to NC delta T. Just like there in calorimetry, we got Q equals to ms delta T. There we were talking in terms of kg mass, here we are talking in terms of mole. The formula remains the same. When you write this formula in the differential format, you write dq equals to nc dt. Now once we have established this, let's utilize this to find the heat capacity for different type of processes. So first of all, my favorite process, which is isochoric process. For an isochoric process, Q equals to delta U plus W from first law, yes. For an isochoric process, work done is 0, yes. For all goddammit process, we can write the change in internal energy to be F by 2 and R delta T. So for isochoric process, the heat given equals to change in internal energy equals to F by 2 and R delta T. So comparing this Q and F by 2 and R delta T and writing them in the differential format, you will write dQ equals to F by 2 and R dt. Now just by comparing these two, we can find what is the molar specific heat for an isochoric process. That is, what is the molar specific heat for a constant volume process. So what to do here? Bring N here and make it look like N into F by 2 into R into dt, so that you can compare. Once you have written the same thing this way, you can now say, okay, NC dt, N something dt. So this something has to be same as the molar specific heat. So we say that the molar specific heat for an isochoric process, that is a constant volume process, is nothing but Fr by 2. Similarly, let's find out molar specific heat for an isobaric process. So if the process is isobaric, we know that the heat given equals to change in internal energy plus work done. The change in internal energy can be written as F by 2 and R delta T for all process. The work done for an isobaric process can be written as P delta V or can be written as NR delta T. So you can take NR delta T common. So the heat given can be written as F by 2 plus 1 into NR delta T. Writing the same thing in differential format, you will write dQ equals to F by 2 plus 1 into NR dt. Now rearrange it, bring the N in front and take everything else apart from dt common. So you get N into F by 2 plus 1 into R into dt. So here dq equals to nc dt, dq equals to n something dt. So this something is the molar specific heat for a constant pressure process, that is isobaric process. So we say Cp comes out to be equals to F by 2 plus 1 into R. Now two things here. If you expand this now, you will say Cp equals to F by 2 into R plus R. So clearly you can see Cp is more than Cv. The molar specific heat at constant pressure is more than the molar specific heat at constant volume. By how much? R. This is more by an amount R. Cv is Fr by 2. Cp is Fr by 2 plus R. So Cp is greater than Cv. And Cp minus Cv, if you do Cp minus Cv, okay? So if you do Fr by 2 plus R minus Fr by 2, what do you get? You get R. So Cp minus Cv equals to R. This particular equation is called Mayer's equation. Okay, Cp minus Cv equals to R, and Cp is greater than Cv. While teaching you about isobaric process, I said that you have to give more amount of heat in case of isobaric process for same rise in temperature. Why? In isochoric process, the volume is constant. So all the heat provided is utilized to increase the internal energy, is utilized to increase the temperature. While in the case of isobaric process, when you provide some heat, some part of that heat is utilized to do work on the surrounding. So the internal energy do not increase by the same amount. So you have to provide more heat to increase the internal energy by the same amount as in the case of isochoric process. Okay, so Cp is more than Cv and Cp minus Cv equals to R. So now let's move on to our other two processes, which is isothermal and adiabatic. So first of all, let's talk about isothermal process. We know that dq equals to nc dt. Yes, so C has to be equals to dq by n dt. So we can write dq equals to nc dt. So the molar specific heat can be written as dq by n dt. For an isothermal process, what is special? Sir, temperature remains constant. So for an isothermal process, temperature remains constant. So dt has to be 0. Now better look here. In this equation, C equals to dq by n dt. If this dt becomes 0, the denominator becomes 0. What will be the value of C? So sir, if the denominator becomes 0, C equals to something by 0. So C has to be equals to infinity. So remember, for constant temperature processes, whether there is phase transformation in calorimetry or whether you have got an isothermal process, for constant temperature processes, the specific heat comes out to be infinity. Now let's talk about adiabatic process. Again, you know that dq can be written as nc dt. So C can be written as dq by n dt. For an adiabatic process, what is so special about adiabatic process? Sir, there is no heat exchange. So dq, this numerator becomes equals to 0. Since the numerator becomes 0, you can say, sir, the molar specific heat for an adiabatic process has to be 0. So for an adiabatic process, dq equals to nc dt. So you can write C equals to dq by n dt. For an adiabatic process, dq is 0. So the numerator here becomes 0. Hence the molar specific heat comes out to be 0. For which process? For adiabatic process. So let's revise everything about molar specific heat once more. So first, for isochoric process, we say that the molar specific heat at constant volume comes out to be Fr by 2. Okay, and this is called Cv. For isobaric process, the molar specific heat comes out to be F by 2 plus 1 into R, and this is called Cp. For adiabatic process, it is 0, and for isothermal process, it comes out to be infinity. Moreover, beta, remember that Cp minus Cv gives us R, the Mayer's equation. And the last thing, we have learned that gamma equals to F by 2 plus 1 upon F by 2. Yes. If I do Cp by Cv, what do I get? Sir, if you do Cp by Cv, then Cp by Cv will be F by 2 plus 1 upon F by 2, which will be equals to Poisson's ratio, also called gamma. And gamma equals to Cp by Cv. So these are all the things you need to know about molar heat capacity. Now, the last thing here, how to deal with mixtures. So the mixture case, and this is really simple. Let's do it quickly. First thing, how do you write molar mass of mixture? If you have got N1 mole of first gas, N2 mole of second gas, N3 mole of third gas, how to write the molar mass of mixture? Very easy. You write molar mass of mixture as N1, M1 plus N2, M2 plus N3, M3 and so on upon N1 plus N2 plus N3. So the number of mole of first gas multiplied by its molar mass plus number of mole of second gas multiplied by its molar mass and so on divided by the total number of moles. How do you write Cp of mixture? Very simple. If you have got multiple gas having N1 mole of first gas, N2 mole of second gas, N3 mole of third gas, and you need to write the Cp of mixture, simply write as N1 Cp1 plus N2 Cp2 plus N3 Cp3 upon N1 plus N2 plus N3, where Cp1 is the molar specific heat at constant pressure for gas 1, Cp2 is the molar specific heat at constant pressure for gas 2 and so on. Similarly, if you need to write Cv mixture, simply write N1 CV1 plus N2 CV2 plus N3 CV3 upon N1 plus N2 plus N3. If you need to write gamma mixture, you can write gamma mixture as CP mixture by CV mixture. That can be written as, divide them, no better. So this denominator get cancelled. So gamma mixture equals to CP mixture by CV mixture. That can be written as N1 CP1 plus N2 CP2 plus N3 CP3 upon N1 CV1 plus N2 CV2 plus N3 CV3. Do not do this mistake of writing gamma mixture as N1 gamma 1 plus N2 gamma 2 plus N3 gamma 3 and so on. Do not do this error. Students many a time use this and get wrong answer. So how to write gamma mixture? Gamma mixture is CP mixture upon CV mixture. That is written this way. But to find gamma mixture, I personally use the degree of freedom method. We can write degree of freedom of mixture equals to N1 F1 plus N2 F2 plus M3 F3 and so on upon N1 plus N2 plus N3. And since we know that gamma equals to F by 2 plus 1 upon F by 2, multiplying both the side in numerator and denominator with 2 by F, 2 by F, we get that gamma equals to 1 plus 2 by F upon 1. So gamma equals to 1 plus 2 by F. So first, if I need to find gamma mixture, I find the degree of freedom of mixture, and then I use that gamma mixture equals to 1 plus 2 by degree of freedom for mixture. So use this particular method. So let's do a question to understand this. What will be gamma for equimolar mixture of monoatomic gas and diatomic gas? Equimolar mixture means same number of moles of monoatomic gas and diatomic gas. Then what will be the gamma for this mixture? So first of all, let's find the degree of freedom for the mixture. So we will say we have n moles of both monoatomic and diatomic gas, n mole of monoatomic and mole of diatomic. The degree of freedom of mixture will be N1 F1 plus N2 F2 upon N1 plus N2. So n into 3 plus n into 5 upon 2n. This becomes beta, numerator becomes 8n, denominator is 2n, so you get 8n by 2n, and that becomes equals to 4. So this is the degree of freedom of mixture. Once you know the degree of freedom of mixture, you can write gamma mixture to be equals to 1 plus 2 by F mixture. Okay, so gamma mixture equals to 1 plus 2 by F mixture. So in place of F mixture, substitute 4. So you get 1 plus 2 by 4. That becomes 1 plus half. That is 3 by 2. Now this is something I recommend you guys to remember. If you have got equimolar mixture of monoatomic and diatomic gas, the gamma of the mixture comes out to be 1.5, 3.2. Remember that gamma mono is 1.66. Gamma dia is 1.4. If you mix them in equal number of mole, it is obvious that gamma mixture must lie somewhere in between. And the beautiful number between 1.4 and 1.66 is 1.5. So this is a data easy to remember. Now that's all in this hour. I know that I have stressed it a lot, but I hope that if you have seen the whole video, you will remember thermodynamics a lot better. See you guys. Bye bye. See you in the next hour. So that's all for now. See you guys in the next hour.